Okay, so we're here to continue talking about rings. What that means is I have one more minor thing to talk about from chapter 12, the introduction to rings, and then we'll move on to the next chapter, which is about more specific types of rings. But the first thing I need to just mention for a little bit is the definition of a subring. So let R be a ring. A subset S, so it's a subset of R, and of course it's not empty, so it's not the empty set, is a subring really the when we attach the prefix sub to anything, what it means is it's a subset and it's the same type of thing. So it's a ring under the same operations as R. So S is a subring if S is a ring and or under the same operations, the same addition and multiplication. As R. Okay. So I need to define this, and I'll give you a few examples, but the concept of a subring is not going to be anywhere nearly as important to us as the concept of a subgroup was in group theory. Okay, so there will be a specific type of subring later that we do care about more, but as a whole, subrings themselves are not as important. So examples. So for example, Z, the integers, is a subring of the real numbers. They both have the standard addition and multiplication, and Z is a ring and it's a subset of R. Let's see what else. Let me mention this. 2Z, the even integers, is a subring of Z. And that's interesting, or depending on your mileage. That's a relevant example because it illustrates something. As we talked about before, Z is a commutative ring with unity. Unity meaning it has a one element. 2Z, while still commutative, it doesn't have one. So Z has a unity element, 2Z doesn't. So just because you're inside of a ring which does have a unity doesn't mean that every subring will have a unity element. However, it is true that if the big ring is commutative, anything that lives inside of it also has to be commutative. All right. Something else that's interesting. So let me look at the big ring will be Z mod 6. So that's as a set 0, 1, 2, 3, 4, and 5 under mod 6 operations. Now I could take let me take the subset consisting just of 0, 2, and 4. So this will be S. But S is the set 0, 2, and 4 under mod 6 operations. So this is a ring. It's closed under addition and multiplication mod 6. You can right. We'll talk about a subring test in a little bit. But what I want to point out is, so this one has a unity element. Z6 has unity 1. The unity element is 1. The multiplicative identity is 1. We don't have 1 in this subring. But on this subring, you can check what happens if I multiply by 4. 0 times 4 is 0. 2 times 4 is 8, but mod 6, that's 2. 4 times 4 is 16. Mod 6, that's 4, because it's 4 bigger than 12, which is a multiple of 6. So, if you look at it, when I multiply by 4, I get the same answer back. I get the same element back. 0 times 4 is 0, 2 times 4 is 2, 4 times 4 is 4. So on this subset, 4, the unity, it does have a unity element, and it's 4. So in the big ring, the unity element's 1. In the subring, the unity element's 4. Now, that seems, initially that seems wrong. Like, how can that happen? Because we said before that if you have a unity element, you can only have a single, it's a unique unity element. You can't have more than one unity element. So it looks like there are 2 unity elements here. But 4 is not a unity element in Z6 because, for example, 4 times 1 is 4. It's not 1. 4 times 3 is 12. Mod 6, that's 0. So it's not 3. And 4 times 5 is 20. Mod 6, that's 2. So 4 doesn't act as a multiplicative identity element on this big set here. It only acts as a multiplicative identity element on this smaller subset. Okay, so Z6 only has a single multiplicative identity, and it's 1. The subring only has a single multiplicative identity element, and it's 4. So subrings, even if both the big ring and the subring have a unity element, there's nothing that says it has to be the same element. Although, if the subring does contain that same unity, it'll have to be a unity in the subring as well. So that's just a interesting example to illustrate some things that can happen with subrings. Let me mention one more example just to have this kind of construction ready. We talked about polynomial rings. So ZX with the brackets, that means we're looking at the set of polynomials in the variable x with coefficients coming from the integers. So these are things like 5 plus, I guess I usually start with the biggest power. X to the x cubed, 4x cubed plus 2x squared minus 8x plus 7, for example. That's a 7. So anything of this form. It's a polynomial in x, so the power in x can be as big as we want, but it's a finite sum of these powers. A subring of that, this is just one example, would be zx squared. What this means is it's the set of polynomials in the expression x squared with coefficients coming from z. So what that means is I can form polynomials with x squared, but so I'm looking at powers of x squared. So I could have like x squared to the 4th with an integer in front of it, say 3, plus x squared cubed with an integer in front of it, like 7. I won't do all of them, but x squared to the 1st, 2x squared to the 1st, plus 5. So that would be a polynomial in x squared. If I simplify it, I get a polynomial with x's, but what I get is always even exponents on the x's. So 3x to the 8th plus 7x to the 6th plus 2x squared plus 5. I can't get, using x squared as my base, using x squared as my base, I can't get odd exponents, because once I have x squared, if I raise it to another power, the resulting exponent on x will be even. All right, so these all live inside of zx, but I don't get everything in zx. So this is a subring. If I have two of these and I add them, I'm only going to have even powers of x. So I guess I should actually write out what this is. Zx squared is the set of polynomials with only even powers. So Zx squared is polynomials with integer coefficients. I won't write that down, but with only even powers of x. So if I only have even powers, when I add two of these things, the resulting polynomial will only have even powers. If I multiply two of these polynomials with only even powers, and you multiply it all out, the resulting powers will still be even. Okay. On the other hand, if I made the set of polynomials with only odd powers, that would not be a subring, because if I multiply like x cubed times x cubed, what am I saying? X. Yeah, x cubed. Yeah, x cubed works. I had a momentary brain issue there. X cubed times x cubed, that's x to the sixth. So you'd leave the set of odd powers. All right, but I just wanted to introduce this kind of idea where I don't have to have just a single variable as my polynomial base. I can have some other expression. All right. So the last thing I want to say about subrings for now is just to mention the subring test. So R is a ring. S is a non-empty subset. So it's not the empty set again. So this is a subring if there's two things I have to check. I'll label them A and B. Well, 1 and 2. All right. So informally, okay, so by the definition, what I have to check would be that S is a ring with the same operations. So really, I have the two operations already established. They already obey all the properties of the ring to be a ring, all the requirements to be a ring. But what I need to check is S is closed under addition, additive inverses, and multiplication. So it needs to be closed under those things. Now, the first two, addition and inverses, that's just the subgroup test. That's just checking that S is a subgroup under addition. And since I have to check multiplication also, it's usually quicker if we use the one-step subgroup test, which amounts to being closed under subtraction. So for any A and B in S, A minus B is an element of S. So you check that the subset is closed under subtraction. That's equivalent to that is the one-step subgroup test for where the operation is addition. And then secondly, I need to check that the subset is closed under multiplication. So for any A and B in S, A times B is in S. Okay, so that's the subring test. I mention it just because later we will care a little bit about subrings, but for now I'm not going to spend any more time on it. I will refer to subrings as we go because they do come up, but they're not anywhere near as important as subgroups. All right, so let's now move on to the next section or chapter 13, I guess. And this is about two special types of rings. All right, so let's start with I mentioned this before, but let's make a definition. A field is, so we mentioned fields. A field is essentially a ring with every reasonable property that we can conceive of, that has all the nice properties. So a field is a commutative ring with unity. So the commutative means that the multiplication operation is commutative. With unity means it has a multiplicative identity element called the unity element, or 1, in which the other property that we want to have is the existence of multiplicative inverses. And like we proved in the previous video, the element 0 can never have an inverse. You can't ever find something to multiply 0 by to get 1, because 0 times anything is always 0. So the best we can hope for is every non-zero element has a multiplicative inverse. So it's a commutative ring with unity in which every non-zero element has a multiplicative inverse. Every non-zero element has a multiplicative inverse. Another way we could say that is every non-zero element is a unit. So if my field is called R, we could say the set of units of R, if you remember the definition of that, that's the set of units. So those are the set of elements that have multiplicative inverses. So the set of units of R would be R minus the 0 element. Everything except for the 0 element is a unit. Right? So, definitions of fields. I already mentioned that, examples of fields. We already went through some of them. Let me mention them again. The real numbers, the rational numbers, the complex numbers. Z, the integers, was not a field because most of the elements don't have inverses. Just 1 and -1 have inverses. I guess the only other one I want to mention right now is Z mod P, where P is a prime. Okay, so for example, let me do it on another board here. If I look at Z mod P, where P is a prime, every element other than 0 will have a multiplicative identity element. So let's just do a specific one. Let's do Z5, I guess. So Z5 as a set, 0, 1, 2, 3, 4. So what I need to do is, other than 0, I need to find, for every element other than 0, I need to come up with an inverse for it. So something to multiply by to give me 1. So I need to be able to fill in this blank for every number other than 0. Well, 1 times 1 is 0. 2, I'm working mod 5, so I need to get to 6. 2 times 3 is 6, which is equal to 1 mod 5. 3 times 2 is 6, which is 1 mod 5. And now, all that's left is 4, so 4 better work for 4. 4 times 4 is 16, mod 5, that's 1. So every single element has a multiplicative inverse. I can do this for any ZP, as long as P is prime. I can't do it for non-prime ZNs. And the reason for this is, so remember that I think we said this before. If you look at U of ZP, this was the set of all K's in ZP, such that the greatest common divisor of P and K is 1. And so the point is, since P is prime, it has no proper factors other than 1. So anything less than P, any number in this set less than P, it can't have any common factors with P other than 1. So the greatest common factor would be 1. But if P is not prime, well, if N's not prime, let me erase. Let me replace P with N. If N is not prime, it has at least one proper factor other than 1. So say it's 2. Say N is even, so it's divisible by 2. Then 2 lives inside of Zn, and its greatest common divisor with N will be 2. So take any prime divisor of N, it's going to be its own, or it's going to be the greatest common divisor with N. So there will be elements that are not relatively prime to N. Those will not be units because of this fact. All right. So ZP, or ZP where P is a prime, those are examples of finite fields. Fields that don't have infinitely many elements. Okay. So, like I said before, a field, and one way of thinking of it is a field is the best possible ring. It's a ring with all of the properties you could hope for. We kind of want to have an intermediate step because it's hard to have every element have an inverse. Then you have examples like the integers, which are still very nice examples of rings. They have nice properties, except they don't have that that property of having the multiplicative inverses. So they're going to be the integers are going to be like the model for this next type of ring that I'm going to define. Before I define that, though, let me define the concept of a zero divisor. In a ring R, a zero divisor is an element, we'll call it A of R, not equal to 0. Let me rewrite that, sorry. Is a non-zero element so A is not 0, such that there exists another non-zero element, so call it B in R, where if I multiply these two non-zero elements, I get 0. So A times B is 0. So a zero divisor is basically, you're saying, I found a way to factor, excuse me, I found a way to factor 0 using non-zero factors. So you can't do this in, for example, the integers. This is impossible in the integers. It's impossible in the real numbers. We're used to dealing with number systems where if I have non-zero things, they always multiply to something other than 0. Non-zero times non-zero will equal non-zero. A zero divisor is an instance where that is contradicted in some ring. Okay, so I'll give you some examples here. All right, so let's look at some examples of zero divisors. We already saw one, I guess, but in Z6, 2 times 3 is 6, but 6 is 0 mod 6. So 2 and 3 are non-zero. They multiply to give you 0, so they're zero divisors. 2 and 3 are zero divisors. In matrices, I can come up with two non-zero matrices that multiply to give me the zero matrix. So let me think for a second. Something like this: 1, 0, 0, 0, and 0, 0, 1, 0. If I multiply these two matrices, they're not the zero matrix because they have at least one thing that's not 0. But if I multiply this, I have 1, 0 times 0, 1. That gives me 0 plus 0. So 0. 1, 0 times 0, 0 is 0. 0, 0 times 0, 1 is 0. And 0, 0 times 0, 0 is 0. So I multiply these two non-zero matrices, I get the zero matrix, the matrix that consists only of zeros. Right? Let me make one more example for now. So if I have a direct sum of rings, in these cases I can always find some zero divisors by putting a 0 in one place and not the other place. And then putting a 0 in a different place in the other element. So here's one element of my direct sum. 0, 1 is one element of this. 1, 0 is a different element of this. They're both non-zero because they don't consist only of zeros. But when I multiply component-wise. 0 times 1 is 0. 1 times 0 is 0. And that's my 0 element for this direct sum ring. So these are both zero divisors. Okay, so we've defined the concept of a zero divisor. Now we can define our next type of ring called an integral domain or an integral domain. The definition is an integral domain, we'll call it D for domain, is, so it's almost, it's like the next best thing to a field. So it's commutative. It's a commutative ring with unity that has no zero divisors. And I'll give you some examples in a second, but let me offer an alternate way of thinking about this last condition. So no zero divisors, let me call that star. this condition star is equivalent to the following more useful property. Like if I want to prove something about integral domains, I want to be able to use this no zero divisors condition in a more straightforward way. So logically, it's equivalent to saying AB equals 0 implies A equals 0 or B equals 0. So if a product equals 0, it implies that one of the factors in the product already has to be 0. So that's one way of saying it. That's the one that we use the most probably. There's a third, which would be the contrapositive of this. Let me call this triple star, which would say if neither of these is 0, A doesn't equal 0 and B doesn't equal 0, then A times B is not equal to 0. Okay, so no zero divisors is a nice short conceptual way of saying it in English, but logically when we're trying to use these properties in a proof or in a problem, these are the two ways that we'd say it. An integral domain is a commutative ring with unity that satisfies any of these equivalent properties. So AB equals 0 implies A equals 0 or B equals 0. All right. So now let's go through some examples, and then maybe in this video I'll start to talk about what the significance of these things is. So examples of integral domains. I'm going to abbreviate. Integral domains. By the way, the integral word, the word integral, derives from integers. So the first example of an integral domain is Z. So Z is an integral domain. I'll maybe prove this separately, but let me just mention it. Any field is an integral domain. So a field is a stronger condition than being an integral domain. If it's a field, it's automatically an integral domain, not vice versa. So Z is an example of an integral domain that's not also a field. All right. Polynomial rings. I'll prove this as well, but if I take a polynomial ring where the coefficients are already an integral domain, then the polynomial ring will also be an integral domain. So dx, where d is an ID already. So not integral examples that are not integral domains. Well, if you go back to what we just got through talking about, zero divisors, any of those examples of zero divisors, the ring that we were talking about for that example can't be an integral domain because we found some zero divisors. So what we have Zn, where n is not prime, like we did with Z6. If n has factors, so if n factors as p times q, then p times q equals n, but mod n, that's 0. So in a non-prime mod situation, there will always be zero divisors that just come from factoring this modulus, or whatever you call it. All right, z plus z. Really, anytime you have a direct sum, let me be careful here. Anytime you have a direct sum of rings where they're all non-trivial rings, meaning they have other things besides the zero element, the resulting direct sum will not be an integral domain. I guess I'll include it, but matrix rings are also not integral domains. So matrix rings like this are not integral domains, partially because we can find zero divisors. But even before that, matrix multiplication is not commutative, so it can't be an integral domain for that reason either. Let's see. Right. So matrix rings are not integral domains. All right. So some of these, like I'll come back and say something more about why these things are definitely integral domains. But let's actually let's start with an easy proof. So let's start with the field fact. So I'll call this a theorem. If F is a field, then F is an integral domain, ID. I should just commit to saying ID. Okay, so to prove something's an integral domain, if we already know it's a ring, I'm not going to prove that it's a ring, we need to check three things. It's commutative, it has a unity, and it has no zero divisors. Okay, so the first two in this situation are immediate. It's a commutative ring and it has a unity because those were among the requirements to be a field. A field was a commutative ring with unity that has this property about multiplicative inverses. So you already got those two for free. The only thing remaining is the no zero divisors property. So I'm going to prove the second version of that property. So let A and B be elements of F. I want to suppose AB equals 0. We assume the product of the two elements is 0. We need to prove that that implies one of the two elements is already 0. So let's assume that A is not 0. So A might be 0. If A were 0, we'd be done. We're trying to prove that one of the two is 0. So let's assume A is not 0. Then we need to show that B has to be 0. So show B equals 0. Okay, so here's the key step. Since we're in a field, if A is not 0, it has an inverse. So since F is a field, A is not 0, A inverse exists. And now I can multiply both sides of the equation by A inverse. A inverse times A gives me 1. A inverse times 0 is 0 because everything times 0 is 0. So therefore B equals 0. So therefore AB equals 0 implies either my assumption was wrong and A equals 0, or my assumption is right, A doesn't equal 0, but in that case B equals 0. So therefore, F satisfies the third requirement to be an ID. And we're done. So any field is an integral domain. Okay, let me go ahead and prove the other big property. Okay, so what's so good about this no zero divisor property? Well, let me say it like this first before I write the theorem. Let's think of the integers in the first place. So suppose we have an equation in the integers, and we say like 5x equals 10. Well, we can say x has to equal 2. And the reason I'm allowed to do that, I mean, it's like I'm dividing both sides by 5, but in the integers, I don't have multiplicative inverses. So it's not really fair to say I'm going to multiply both sides of this equation by 1/5. Because I'm working in the integers, 1/5 doesn't exist. So what I'm actually doing here is I'm saying it happens to be true that 10 equals 5 times 2. And what I'm doing is I'm canceling 5. Like if I said 5x equals 8, I can't say x equals 8 over 5 because that's not an integer. I'm looking for an integer that satisfies the equation. So I'd just be stuck with 5x equals 8 and there wouldn't be a solution. Okay. So what allows me to cancel is the fact that z is an integral domain, as we'll prove with the next theorem. And this will be the last thing in this video. I'll continue integral domain stuff in the next video. So this is the cancellation property in integral domains, IDs. So let's assume let D be an integral domain. For A, B, and C in the set D, we have the following property. If AB equals AC and A is not 0. So if A times B equals A times C, and we know A is not 0, then I'm free to cancel the A's and conclude that B equals C. So just like I did in the integer example, I'm allowed to divide by non-zero elements if I have that same element on both sides of the equation. Okay, so let's prove this. Use up too much space writing it up, but you'll still have it in front of you, hopefully. So let's prove this theorem. So we have the same setup. Suppose D is an integral domain, A, B, and C are non-zero. So let's suppose, A is non-zero. Suppose A is not 0 and AB equals AC. Okay. I don't have inverses, so I can't multiply by A inverse. But I can subtract. So I'm working with an equation. I can subtract AC from both sides. So AB minus AC equals 0. Both of these have an A. By the distributive property of rings, I can pull out an a and say a times b minus c equals 0. And now what we have here is a factorization of 0. 0 breaks up as a times b minus c. And that, by the no zero divisor property of IDs, that implies one of the two factors in this product has to be 0. So a equals 0 or b minus c equals 0. However, we've already assumed that a is not 0. Since a is not 0, it must be the case that b minus c is 0. And if that's the case, I can add c to both sides. So b equals c, and we're done. That's what we're trying to prove, is that when ab equals ac, we can conclude b equals c when a is not 0. All right, so again, big picture of this theorem, this property, is that when you're working in an integral domain, you don't necessarily have inverses. You don't have inverses of elements, but you're still free to cancel them. If you have that same factor in both sides of an equation, you can cancel that factor. So you can divide by common factors. All right, I guess I don't need to erase on camera. All right, so I will continue this chapter in another video where we'll be talking about other concepts within integral domains and related things.